Yes, am I audible?
Yes, sir.
So in the last class, we have finished this semiconductors. Now, there is one chapter in the first book, which is natural magnetism. So we haven't finished this chapter while we are doing first book. So let's start with that. This bar magnet is repetition of electrostatics. Whatever you did in electrostatics with electric dipole, you can repeat that with a bar magnet. So we do bar magnet just by taking analog from the electrostat. Like in electrostat, wherever you use 1 over 4 pi epsilon naught. For a bar magnet, we use mu naught by 4 pi. In electrostat, wherever we use dipole moment, electric dipole moment, instead of electric dipole moment, here we use magnetic dipole moment. So these are analog. Like if you know the results for a electric dipole, you can write results for a bar magnet. So the first thing we start is magnetic pole strength. Magnetic, or it would be better if I take analog. So let's make a table. On the left hand side, we will write terms which we did in electrostat, and in the right hand side, we will write terms for a bar magnet. Electrostatics. Some authors this branch as magnetostatics also. Magnetostatics. So just like electrostatics was the study of electric charge at rest, magnetostatics is the study of a magnetic pole at rest. So the first term in electrostatics is a charge. So instead of charge, we use magnetic pole strength here. Instead of charge, we use magnetic pole strength. So we represent electric charge by Q. We represent magnetic pole strength with M. So we have two types of magnetic pole strength, one for the north pole, another for the south. So this is small m for the north pole and small m for the south pole. Its SI unit is ampere meter. Ampere meter. Second is electric dipole moment. Electric dipole moment. So in electrostat, we have electric dipole moment. Instead of electric dipole moment, in magnetism, we use magnetic moment. We use magnetic moment. See, what is magnetic moment? If you take a bar magnet, we take a bar magnet. This is north pole and this is the south pole. The pole strength here is small m. Pole strength here is small m. The length between the north pole and the south pole is L. So the magnetic moment we represent is represented by capital M, which is the product of pole strength multiplied by the length of dipole, means the separation between the north pole and the south. That is the magnetic. So its SI unit is, see, the SI unit of magnetic pole strength is ampere meter and this is length. So this will be ampere meter into meter. So it will become ampere meter square. This is magnetic. This L here is known as length of dipole also. Length of dipole. There is one more name for it, which is it is also known as magnetic length for the dipole. After magnetic moment, the third thing that we did in electric dipole was electric field on axial line of dipole. Electric field on axial line. See, there's no need to derive these results. These are direct results. You just have to remember. There's one more thing. This magnetic moment is a vector quantity. Its direction is from south to north. So the direction of magnetic moment is from south to north. South to north. This is the direction of magnetic. Next, we have electric field on the axial line of bar magnet. So if you have a bar magnet, this is south pole and this is north pole. We take a point here. So the separation between the center of the bar magnet and the point is, let's say, some r. Say that this separation is r. Sorry. So for electric dipole, right? This is plus q. This is minus q. Separation between plus q and minus q is 2a. We take a point here and take separation from the center of the dipole to the point. The expression of electric field was k into 2p divided by r. This was an electrostat. When we repeat the same thing for a bar magnet, we call it magnetic field. Magnetic field on axial line of bar magnet. So if you take a bar magnet, this is south pole and this is north pole, and you take a point here. This point is on the axial line, on the axis of bar magnet. Yeah. So the magnetic field, the expression of magnetic field over this point is B is it's mu naught by 4 pi. It's 2m by r cube. This is the expression of magnetic field on the axial line. And from this expression, you can guess the direction of magnetic field also. See, this is magnetic field and this is magnetic moment. On the left hand side, you have magnetic field. On the right hand side, you have magnetic moment. That means direction of magnetic field is same as that of magnetic moment. What is the direction of magnetic moment, Hishma? Hishma, what is the direction of magnetic moment? Nazia, what is the direction of magnetic moment?
South to north.
South to north. This is the direction of magnetic moment. So this expression says that on axial line, the direction of magnetic field is same as that of magnetic. So if magnetic moment is acting to the right hand side, magnetic field is also to the right hand side. So direction of field is same as that of magnetic on the axial line. And there was one more thing which was on equatorial line. In electrostat, the result was if you have plus q charge here, minus q charge here. What does equatorial line means, Sakina Abbas? Ishma, what does equatorial line means for an electric dipole? Yashika, what does equatorial line means for a dipole?
They're the x-axis.
No, equatorial line means the perpendicular bisector. Equatorial line means perpendicular bisector. Here, this is the equatorial line. So if we calculate magnetic field on equatorial line of bar magnet. Magnetic field on equatorial line of bar magnet. So if you take a bar magnet here, this is south pole and this is north pole. This is the equatorial line. Huh? You want to calculate magnetic field here. So on the equatorial lines, this is the direction of magnetic movement from south to north. On equatorial line, the expression of magnetic field is it's mu naught by 4 pi. It's mu naught by 4 pi minus of m divided by r. This minus sign shows that the direction of magnetic field on the equatorial line is opposite to that of magnetic movement. Equatorial line is perpendicular bisector. So this is the direction of magnetic field. This direction is opposite to that of magnetic. After equatorial line, the next is fifth. Torque on electric dipole in uniform field. Torque on electric dipole in uniform. So analog to this, in for a bar magnet, we calculate torque on a bar magnet. Now here, instead of bar magnet, he can give a magnetic needle also. So bar magnet or magnetic needle will have same result. Or magnetic needle placed in uniform magnetic field. Placed in a uniform. Placed in a uniform magnetic. So if you take a bar magnet and you place that bar magnet in a uniform magnetic field, this is uniform magnetic field. You take a bar magnet and you place that bar magnet in the uniform. This is south pole and this is north. This is the direction of magnetic movement. This is the angle theta. The torque on the bar magnet is m cross. We derived this expression in chapter number 4 also. This was for a current carrying coil in uniform magnetic field. The torque is this. Torque is m cross b. When you open this expression, it comes out to be torque is mp sine theta. Sixth, potential energy of dipole in uniform. Potential energy of dipole in uniform. So here we use potential energy of bar magnet in uniform magnetic field. So this is a uniform field. In uniform field, we place a bar magnet here. This is south pole, this is north, at an angle theta. So due to interaction of the bar magnet with the field, the system will have some potential energy, which is minus of m dot b. And this is minus of m dot b. See, this section is the repetition of electric dipole. If you know electric dipole, that means you know this bar magnet. And there are very less chances of getting questions from this particular section in your course exams. In magnetics, the major portion is that magnetic effect of current and force on a charged particle in magnetic field. Note it down. They'll see what type of questions you can get on this section. So this chapter have two sections. One is this magnetostatics. Another is classification of magnetic medium. Earlier, earth magnetism was also in syllabus, but this year earth magnetism is not a part of your syllabus. Note it down. We'll see how type of numericals you can get on this term. Please note it down. Yashika, Noha, your pre-boards are over.
No, sir.
No, sir.
So when is physics pre-board of physics?
Sir, I've had physics, but the others are left.
Okay. And Noah, yours? Your physics pre-board is over or it's still there?
Sir, it's on 24th January.
24th. Just 1 second. Just 1 second. Tell me once you have written, I've scrolled.
Sir, done.
On the left hand side, I just have written just for the reference. Huh? Nabil, we have started natural magnetism. Huh? So we're doing bar magnet current. This is portion of chapter number 5. Huh? Sorry, forgot to write. This is chapter number 5 of NCERT. Yashika, how was your exam, physics exam?
Sir, it went well.
Sir, could you
Nice.
scroll to the top of the page?
Yes. Was there any question that you want to discuss with me? You have confusion or something? Any numerical, any conceptual question?
Not as of now, sir.
See, if in your pre-boards you came across any question which you can't solve at that time, and even after opening your copy, you're not able to solve that question, just share that question on the group. Huh? Just share that question on the WhatsApp.
Yes, sir.
Nabil, can I scroll down?
Just a minute, sir.
So magnetic pole strength is just like charge, huh? The analog of charge. In electricity, we use charge. In magnetism, we use magnetic pole strength, like the pole strength of north pole and the pole strength of south. So Magnetic moment is just the analog of electric dipole moment. In electric dipole moment, we'll take charge and length. Here we take magnetic moment. Can I scroll? Even in your revision, do this chapter at the end only. The type of questions that come from this chapter are very theoretical. We'll discuss after this section the classification of magnetic material. Or a theoretical portion. Just have to memorize some properties of dia, para, and ferromagnetic material. Even if you look at PYQ, the majority of questions are from the classification of magnetic material. You don't ask many questions from this section. Rishma, are you still in class?
Yes, sir.
Arpit, you are again late, huh?
Sir, I was having my dinner.
तेरा डिनर कभी भी हो जाता है ना? पिछली बार 10
सर
बजे
केमिस्ट्री क्लास होती है सर इससे पहले,
अभी डिनर कर रहा था.
फिर यहाँ से सर 10:30 हो जाते हैं.
Can I scroll it? Nabil, Ishma, Sakina Abbas.
Yes, sir.
Yes, sir.
Written.
Yes, sir.
So that was on the axial line, and then take it on the equatorial line. So Arpit, there are two parts in this chapter. One is bar magnet that you have missed. Now just wait for 10-15 minutes for the second part. Second part is classification of magnetic material. Let's start the second part. Tell me once you have written, I'll scroll it. Okay, there is one news. In interference, the derivation of Young's-Double-Slit experiment is not a part of syllabus. We did an entire derivation of YDSC that's not in syllabus now. Only the final expression of fringe width and those conditions of bright and dark fringe, that is a part of syllabus. The derivation is not a part of syllabus. So while you are revising, you can save some time from.
The diffraction, the derivation is there.
Just give me 1 second. I have updated syllabus. Diffraction. In diffraction also they have written its qualitative treatment only. So, but at least study the width of the central maximum. Qualitative treatment means they're not going to ask any numerical on it. I don't know what they're doing with the syllabus.
Sir,
Yes.
sir, in the capacitor, sir, only the derivation of the energy stored in capacitor is deleted, right? Rest is all the part of syllabus.
In capacitor, the derivation of what?
Sir, the energy stored in a capacitor.
Yeah. There's no derivation of energy stored in capacitor in your syllabus. Only the formula is there. If you want, I can share the screenshot also. Just give me one.
Yes, sir.
See, we did many things in during the class lectures which were not in CBSE syllabus, just because along with CBSE, I was supposed to train you for NEET and JEE also. So almost all theory is being covered. I just have to cover some type of numericals for you.
Sir, you said you send the numericals, which ones are necessary?
Yes, Nabil, I will do it too. I will do it today.
Yes, sir.
Just busy with some other batches. So I have shared a screenshot. You can go through it. Can I scroll it now?
Yes, sir.
See, when you are revising your syllabus for
Sir, can you
CBSE,
scroll up just a minute?
yes, when you're revising your syllabus for CBSE, just strict on the syllabus. The portion whose derivation is not in syllabus, don't do it for school exam. But yes, you will need those derivations for your entrances. You can handle modification only if you know derivations. By just looking at formula, can't handle modifications.
Done, sir.
Now let's see what type of questions you can get from this. And just note it somewhere, like instead of bar magnet, this whole theory is valid for a magnetic needle also. Not just bar magnet. It is valid for any magnet, any type of magnet. That could be a magnetic needle, that could be a current carrying coil, whatever you have. Even for a solenoid, you can write these type of things. So whenever you have a magnet, means something which have North Pole and South Pole, all these 6 terms are valid. Let's do what type of questions you can get from this calculation. The first type of question is on the calculation of field on axial line or on the equatorial line. For those type of questions, just have to decide whether a given point lies on the axial line or it lies on the equatorial line. So let's start with this example. say you have two bar magnets. One is this is south pole, this is north. This is the direction of magnetic moment M1. Then you have another bar magnet. This is it. This is placed in this way. This is south pole, this is north pole. This is the direction of its magnetic moment M2. So you have two magnets. You're supposed to calculate magnetic field here. Okay, let's solve this numerical together. Sakina Abbas, let's start from you. Sakina, this the easiest question. Just tell me at this point P, the contribution of magnetic field will come from a single bar magnet, will come from both the bar magnets.
Both the bar magnet.
Both the bar magnets. Nazia, for the first bar magnet, this one. This point P lies on the axial line or it lies on the equatorial line?
First bar magnet, it is axial line.
Axial line. See, axial line means just extend this line joining the south pole and north pole of the magnet. So if point lies anywhere on this line, it is on the axial line. So for first bar magnet, the point lies on axial line. So at P, both will generate magnetic field. So for the first one, the magnetic field is for the first bar magnet on the axial. Plus, this is magnetic field due to the second bar magnet. For second bar magnet, Noha, this point P lies on the axial line or on the equatorial line?
Sir, equatorial line.
Equatorial. See, for the second magnet, this is the axial line, but the point is perpendicular to it. So point lies on the equatorial. So this is P2 equal. So the net magnetic field is the sum of magnetic field due to each magnet. So this is first magnet. This is point P. Separation is R. The magnetic field is it's mu naught by 4 pi 2m1 by R. Now let's decide the direction. I just have written the magnitude. Now I write the directions also. For the first bar magnet, what will be the direction of magnetic field on axial line? It's same as that of magnetic moment. So see, magnetic moment is to the right hand side. That means magnetic field is also to the right hand side. Let's do it again. We have to decide the direction of magnetic field due to the first bar magnet at point P. To decide direction, first check the direction of magnetic moment. What is the direction of magnetic moment? South to north. Magnetic moment is to the right. The direction of magnetic field on the axial line is same as that of magnetic moment. If your magnetic moment is to the right hand side, field is also to the right hand side. So this is B1, mu naught by 4 pi 2m1 by R. What unit vector you will use for B1, Arpit? I, J, K, which unit vector you will use for B1?
I cap.
I cap. Now let's do second one. For the second one, this point P lies on the equatorial line. So expression of magnetic field on the equatorial line is it's mu naught by 4 pi m by r cube. There is one negative sign also, but that negative sign will help you in deciding the direction. Right now, I'm writing just the magnitude. To get the direction of magnetic field here, again, first of all, check the direction of magnetic movement. What is magnetic movement? It's downwards. Hishma, what is the direction of magnetic field on the equatorial line? Is it same as that of magnetic moment or opposite to that of magnetic? Hishma. Direction is same as that of magnetic moment or opposite to that of magnetic?
Same as that of magnet.
Same. Just check the expression. See, this is the expression. Just check this expression now. Tell me. On equatorial line, P and M are in same direction or in opposite direction? Hishma.
Opposite direction.
Why opposite now?
Because it's the negative sign.
Negative sign. So if M2 is downward, see, the magnetic field will be upwards that speed. So upward means positive y-axis means j. This is how we calculate. This is the first type of question that you can get on bar magnet. Some bar magnet will be given. You are supposed to calculate the field on the axial line and the equatorial. Do it. Is it clear, everyone? Noha, Yashika, Arpit?
Yes, sir.
Yes, sir.
See, this is just the repetition of electric dipole. If you can remember, we did these type of questions for electric dipole also. If you just turn your pages and go to that class lectures of electric dipole, we did same questions for electric dipole also. Same you can repeat for bar magnet. Instead of bar magnet, you can get a magnetic needle also. The same thing. You can repeat the same thing for magnetic dipole also. Yes, can I scroll it now? Nabil, Arpit, Chicken Abbas.
Yes, sir.
The second type of question that you can get here is based on SHM. Now, this question is repeated many times in boards. The question says, show that this is this question is repeated many times. Motion of bar magnet. And this is again repetition of electrostat. We did this question in electrostat also. Repetition of bar magnet or magnetic needle in uniform magnetic field is SHM. Calculate time period and frequency. So see, this is the magnetic field, and in this magnetic field, you can put a bar magnet. South pole analysis. You have to show that this bar magnet will undergo SHM. For SHM, just have to prove that it will oscillate. See what happens. When you put this bar magnet into a magnetic field, it will experience a torque. What is the expression of that torque, Arpit?
Sir, MB, M cross B.
M cross B. If you open it, it will be M cross B will be MB sine theta. This is the torque acting on the dipole. So due to this torque, it will try to align itself in the direction of field, but it will overshoot its mean position due to momentum it gained. Then again, the torque will act and it will again try to align the dipole in the direction of magnetic field. And due to this torque, it will keep on oscillating about the magnetic field. So this is the torque which is MB sine theta. If we consider small oscillations, if we consider small oscillations, oscillations, which means sine theta is approximately equal to theta. Then you can write torque is equal to mb theta. Here m and b are constant. This m is magnetic moment and b is magnetic field. When the dipole oscillate, this m and b will not change. So you can write this as tau is equal to k theta. And this is the equation of SHM. This equation shows that your dipole will be in SHM, simple harmonic motion. So instead of where k is mb. Now you have to calculate the angular frequency. The angular frequency omega is its root over k by m. So it's root over mb divided by. This is the angle. You can also calculate the time period of oscillation. Angular frequency is 2 pi by time period, which is mb by m. This is it. Note it down. Yes, sir, it's active. Can I scroll it?
So wait a second.
You all should switch on the video like Arpit. So use focus mode so your video will not come into the recordings, nor you can see each other.
Again, scroll.
This is an important question. Yes, can I scroll it?
Yes, sir.
So these are the type of questions that you can get from this bar magnet. The next topic is very, very theoretical. The next topic is classification of magnetic material. See, there is one more topic in NCERT, which is Bohr magneton. So Bohr magneton is not in syllabus, but to understand classification of magnetic material, you should know what does Bohr magneton. So I'm just giving a very brief introduction of Bohr magneton. What does Bohr magneton? This is not in CBSE syllabus now. Bohr magneton, once this was in syllabus, this is given in NCERT, but it's not a part of syllabus. So I'm not going to derive. Bohr magneton means if, say, you have an atom, this have nucleus, and electrons are revolving around it. This is the Bohr's model. Can you name some sources of magnetic field, Arpit? Some sources of magnetic field. What?
Bar
Three sources.
magnet.
Bar magnet and
Circular,
Earth magnet.
so
Earth
current,
magnet.
circular current loop.
Current carrying loop. If you have a current carrying loop, if you have something which have current, then that will behave like a magnet also. So if we talk about an atom, in an atom you have nucleus at the center and electrons are revolving around it. So these revolving electrons will contribute to current, right? What is current? It's nothing but flow of charge. It does not matter whether that charge is flowing in a wire or it is flowing in a conductor or it is flowing in an atom. So if electrons are revolving around the nucleus, then due to the motion of electrons, you will have current. This is current. Due to the motion of electrons, you will have current. And if you have current, that means you have magnetic field. So this current will contribute to magnetic field. So through Bohr magneton, you try to calculate the magnetic field of this revolving electron. Bohr magneton is basically the magnetic moment, minimum magnetic moment associated with this electron. But it's related to the magnetic field of electron. So by the calculation of Bohr magneton, the conclusion is if you have an atom in which electrons are revolving around the nucleus, due to revolution of electrons, you get magnetic. So each electron will have some magnetic field. Each electron will behave like a magnet. It will have south pole as well as north pole. So each electron is a source of magnetic field. This will have south pole as well as north pole. It's behaving like a dipole. Now, if each electron is behaving like a dipole, then atom should have some magnetic moment. It have various electrons, so it should have some magnetic moment. So everything should be magnetized. If we extend this theory, that means each and every object should be magnetized. This pen should be magnetized. Like this pen and this cup should attract each other because this pen is made up of atom. This atom had millions of electrons. Every electron is a magnet. Similarly, this cup is made up of atom. Atom have electrons. Every electron is a magnet. They should attract each other, but they're not attracting. What does that mean? You can conclude it in two ways. The one is in an atom, various electrons can cancel each other magnetically. So if you have an atom, you have two electrons. There is one possibility that one and two electrons can cancel each other's magnet. So due to cancellation, the atom will not have any magnet. Or I can say that atom will not have any magnetic. The second possibility is electrons gets added up. Atom have some magnetic moment, but in a cluster, like if I take this pen will have billions of atoms. One atom can cancel the magnetic moment of another atom. And then again, it will be non-magnetized. So each electron is a magnet in itself. Each electron have a non-zero magnetic moment. But when these electrons are in an atom, then there are two possibilities. One possibility is one electron can cancel the magnetic moment of another electron. This happens in a diamagnetic material. So if you take a diamagnetic atom, then one electron will cancel the magnetic moment of another electron. Or the magnetic moments of electrons get added up. So your atom will have some magnetic moment. But when you take cluster of atoms, then one atom will cancel the magnetic moment of another atom. This happens in the paramagnetic material. or in a ferromagnetic. If you take a single atom of iron, the single atom of iron is a magnet. The single atom of iron have north pole and south pole. But when various atoms of iron comes together, they just cancel out each other's magnetic. So the conclusion is each electron is a magnet. Each electron have some non-zero magnetic moment. Atom of a diamagnetic material is not a magnet. It does not have any magnetic moment, but atom of a paramagnetic and ferromagnetic material have some magnetic moment. So from here, the classification starts. The classification of magnetic material. This one. From here, the classification starts. The classification of magnetic material. So the materials that you have can be classified into three types: diamagnetic material, paramagnetic material, ferromagnetic material. So to classify materials on the basis of into diamagnetic, paramagnetic, or ferromagnetic, you should know some definitions. We have discussed these things in magnetic effect of current also, but these are specific definitions like magnetizing field or magnetic intensity. By magnetizing field or magnetic intensity, we refer to external factor. We refer to some external factor which can magnetize the material, which is usually current. Again, see, the magnetic field in a material can come from two contributions. It can have contribution from a single atom also, or it can have a contribution by external factor also. Like if you have a wire, you pass current through the wire, then that current can generate magnetic field. That current is an external factor. Second contribution could be from the individual atoms itself. Like this material will have some atoms. These atoms can also contribute to magnetic. So the contribution of magnetic field,
Sir,
yes, I'm repeating again, can come from the two factor. One is external. Second, it could be internal. When you say external, it's usually current. Current is an external factor. When you pass current through a wire, it generates magnetic field. So the magnetic field is due to current, not due to the atoms of the wire or something. The second could be an internal factor. This is due to the contribution of atoms. Individual atoms of the material can also contribute to magnetic. So these are the two sources from which you can get magnetic. Yes, Arpit, you were saying something.
sir, I was asking like we can also magnetize a material with the help of a magnet also.
Yeah, that's again external force. If that external magnetic field which helps you in magnetization of materials in external force. This is what
Okay,
happens
sir.
in a solenoid, right? You take an iron piece of iron, you
Yes, sir.
walk some wire over it, you pass current through, and this iron becomes magnetized. So magnetizing field is represented by H, which is B magnetic field by mu naught. Its SI unit is ampere meter. Simply, this is an external factor. Intensity of magnetization. When we talk about intensity of magnetization, that means we are talking about the internal factors which can contribute to magnetic. We are talking about the internal factors. Internal factors are like atoms, individual atoms. We define intensity of magnetization in this way. This is the ratio of magnetic moment of the sample divided by volume. Like you have a sample, you have various atoms. The magnetic moment of all the atoms is in same direction. So this sample will have some net magnetic moment. You take this magnetic moment divided by the volume of the sample. This is intensity of magnetization. So these are two factors. This is huge external factor, which could be current, and this is internal factor, which are usually the atoms. The magnetic field from this external factor can be written as mu naught H, and magnetic field due to the internal factors can be written as mu naught I. I'm repeating again, this magnetic field is due to current or external factor. This magnetic field is due to the magnetization of the material itself, internal factor. This magnetic field have contributions from individual atoms and molecules. This magnetic field have contribution from the external magnetizing. Then there is another term, susceptibility. Definition wise, susceptibility is just the ratio of I and H. So susceptibility is just the ratio of intensity of magnetization and magnetizing force. But it tells which material can be easily magnetized. Like if you take iron and gold, you place both iron and gold, you pass same current through iron and gold. Iron will get easily magnetized than gold. So the susceptibility of iron is higher than that. So just tell the ease with which
Sir,
a material can be
which
magnetized in
one?
external field.
Sir,
Yes,
which one is for the external factor, sir? B is equal to mu zero I or B is equal to mu zero H?
mu zero H. This is the external factor and this is the internal factor. This is the contribution from current or this, and this is the contribution from individual atom. So magnetic susceptibility will tells you which material can be easily magnetized in an external magnet. Like if you, I gave the example of iron and gold. You take iron and gold, pieces of same dimensions, exactly identical piece. You pass same current through iron, you same current through gold. Then you switch off the current. Iron will become a magnet. It will have strong magnetic field, but not gold. So material will get magnetized or not will depend upon the nature also. So the nature is given by the susceptibility. Different materials will have different susceptibility. Then you have relative permeability, which is permeability of medium divided by permeability of free space. And then there is one relation between them, this relation. Mu r is 1 plus chi. No need to do these calculations. You should know this relation. Relative permeability is 1 plus susceptibility of magnetic material. So if you have a material having high susceptibility, this will have high susceptibility, it will have relative permeability as well. Note it down. At least note down the points that I am writing here. I will share these notes with you, but at least note down these points that I'm writing. From these definitions, two things should be very clear. One is the external factor, which can contribute to magnetic field, which could be current, and the another is the internal factor, which can contribute to magnetic field, which is usually the contribution from the individual atom. If you can remember, when we take a solenoid, the magnetic field for a solenoid was mu naught Ni. This was for a solenoid when the core was air. But when we placed an iron piece into the solenoid, we write this as mu r, mu naught Ni. Magnetic field increases. So from where does that external magnetic field comes from? That comes from the atoms of the material. When you insert an iron rod into the solenoid, the atoms of the iron will contribute to magnetic field. So if you take a solenoid, its core is air, say magnetic field is 1 Tesla. When you insert an iron rod, the core is iron now, the magnetic field becomes 1000 Tesla. So from where that 999 Tesla comes from? That comes from the individual atoms itself. Note it down. Huh?
So we have to write the whole definition.
Not the whole definition, only the points that I have written. I'm sharing the PDF with you. Share PDF on group also. This one.
Sir, could you zoom out?
Just one. Yes, second. So I've shared the assignments on group also. I'm sharing these notes on group. Can you scroll it now if you have written? Arpit, Hishma, Nabil.
Yes, sir.
Now just note down the expression of relative permeability and this relation between mu r and susceptibility. Oh, you must have written it. So now let's classify materials on the basis of in terms of diamagnetic, paramagnetic, and ferromagnetic. See, for all these classifications, remember few things in mind. Diamagnetic are those materials which get magnetized in the direction of field. Magnetized in the direction of field means they are repelled by a magnet. A magnet will, diamagnetic materials are magnetized in a direction opposite to that of. They magnetized in a direction opposite to that of. Opposite to field. They get magnetized along the field. And ferromagnetic also, they will get magnetized along the field. So due to this statement that diamagnetic material gets magnetized in a direction opposite to that of field, it will repel a magnet. So all its properties are due to repulsion. It will repel a magnet. Paramagnetic material will get magnetized in the direction of field. So they get attracted by a magnet. Ferromagnetic material also get magnetized in the direction of field. So they get also attracted by a magnet. Para and ferro will have same type of properties, but the properties of ferro will be very, very strong as compared to para. That's the difference. So let's start one by one. So you can skip few properties, like you can skip this one. No need to do it. This, if you place a substance in uniform magnetic field, like if you place a diamagnetic material, then magnetic field will oppose it. That means very few magnetic field lines will pass through the diamagnetic material. The majority of field lines will prefer not to pass through diamagnetic material. You can see from here, like there are very few field lines which are passing through the diamagnetic material because it's opposed magnetic. Instead of dia, if you take para, then it gets attracted by the magnetic field. You can see more number of field lines are passing through it. In terms of ferro, more number of field lines will pass through it. So magnetization in ferro will be the maximum, in para will be less than this ferro, and in dia it will be least. So B magnetic field, BM means magnetic field within the material, and B naught means magnetic field in air. So in material, magnetic field is less than air. Here in material, magnetic field is greater than air. Here magnetic field is very, very greater than air. All these properties are due to the simple fact that it repel magnetic field, it repel a magnet, it gets attracted by a magnet, and it attracted by a magnet very, very strong. You can leave this IH curve, no one is going to ask this. Now, temperature. Susceptibility of a diamagnetic material is small, it's negative, and it's independent of temperature. It does not depend upon temperature. Like even if you change temperature, susceptibility will not change. It does not depend on temperature. It's small, negative, and it's independent of temperature. These are the type of questions which are usually asked in exams. Like, what is the susceptibility of a diamagnetic material? It's small, it's negative, and it's independent of temperature. If you change the temperature of a diamagnetic material, nothing will happen. If you comes to paramagnetic material, susceptibility is small, it's positive, and it's inversely proportional to temperature. Like when you increase temperature, the susceptibility will decrease. That's Curie law. When you talk about ferromagnetic material, susceptibility is very large, it's positive, and it depends upon temperature. Here we don't use Curie law, we use Curie-Weiss law. Susceptibility is 1 by T minus Tc. Tc is Curie temperature. Curie temperature means the temperature at which ferromagnetic material gets converted into this paramagnetic material. So for iron, Curie temperature is 770 degrees Celsius or 1043 Kelvin. Means if you heat iron up to this temperature, then iron will get converted into the paramagnetic material. So the type of questions that comes here are just simple. Does diamagnetic material depends upon temperature? No, it's independent of temperature. What happens with paramagnetic? The magnetic behavior decreases. What happens with ferromagnetic? Magnetic material decreases. At a temperature which is known as Curie temperature, the ferromagnetic get converted into paramagnetic. The next, you can ask about mu r. See, we did write this expression that mu r is 1 plus chi. So if chi is small, that means mu r is small. Mu r is in between 0 and 1. Here mu r is in between 2 and 1, and it's very, very high. Like it's around 1000 for ferromagnetic. Magnetic moment of single atom. See, atoms do not have any permanent magnetic moment because here this is cancellation of electron and electron. In paramagnetic material, atoms have some magnetic moment, but they cancel out each other magnetic. That's why the magnetic moment is 0. If you take a single atom of a paramagnetic material, then it's a magnet. It's magnetized. But if you take a cluster of atoms, then they will cancel each other's magnet. And in ferromagnetic materials, atoms have permanent magnetic moment, which are organized in domains. Domains means you have clusters having magnetic moment in same direction. You can draw domains in this clusters, which have magnetic moment in same direction. Clusters means you have millions of atoms which have magnetic moment in same direction. This is one domain. This is another domain. They will cancel out each other. This is another domain. This is another domain. So in paramagnetic, the cancellation is from individual atoms. But in ferromagnetic, the cancellation of domains. Domains means millions of atoms, clusters of atoms having magnetic moment in one direction. Then behavior in non-uniform magnetic field. See, if you take two magnets, North Pole and South Pole, and you place them at a large distance, then at here, the field is strong. And in center, the field is weak. So if you take a diamagnetic material, then it will move from the stronger part of field to the weaker part. So here, if you take a powder of diamagnetic material and you place that powder in a container, the level is same. When you place this container here, then the diamagnetic material will move from the stronger part of the field to the weaker part. So here it will accumulate. But when you put this the magnet of the pieces of magnets closer, then here the field is strong. So it will move from the stronger part to the weaker part. You can see here, it gets accumulated. So here the density is more than the central region. So diamagnetic material move from the stronger part of field to the weaker part. Paramagnetic does just reverse. This is the weak field, so it will move from weak to strong. Here also, it will move from weak to strong. The same thing is for ferromagnetic, but it's attracted strong. Similarly here, if you take a liquid of a diamagnetic material and you put magnetic field here, then this magnetic field will repel the diamagnetic liquid. The level will go down here and level will rise here. But if you connect this with a paramagnetic material, like you have a liquid of, this is paramagnetic liquid in a U-tube, and you connected the magnet, then this magnetic field will attract this liquid. It will go up. The same thing will happen in ferromagnetic material. Similarly, here, if you take a rod of some diamagnetic material, you place that rod in a magnetic field, the rod will align itself perpendicular to the magnetic field. But if you take a rod of paramagnetic material, it will align itself in the direction of field, which shows attraction. Here also it gets aligned in the direction of field, which shows attraction. M is magnetization, H is the external factor, M is very less and opposite to H, means it gets magnetized in a direction opposite to that of field. Here M is low, but in the direction of H, M is very high in the direction of H. Both gets attracted. These are few examples of diamagnetic, paramagnetic, and ferromagnetic. This was it. Then we have one more topic, that is magnetic hysteresis. So just give me one. So no need to write these terms. These are just the definitions. But if you go to the previous year's questions, all questions from this chapter are from this table only. This table, this is very, very important. These values, these properties, this one, this U-tube, all are being asked in exams. Next, we have one thing which is known as hysteresis. So to understand hysteresis, see here. See, this is a ferromagnetic material. And these are the domains here. These are the domains here. So I am not applying any external magnetic field. So H is 0. What is the net magnetic moment of this sample, Nabil?
0.
It's 0.
0.
So all will cancel out each other's magnetic moment. The net magnetic moment is 0. Now what we do, we apply an external field H here. So this field will magnetize the material, means it will rotate these atoms or molecules and try to align them in the direction. So the number of domains which are in the direction of field, its number will increase. So this is it. So the number of domains in the direction of field will increase. So you will have some net magnetic moment in the direction of field. So M naught is now non-zero. If you increase H, more domains will get aligned in direction of field. And then a time will come when all domains will get aligned in the direction of field. Means your material is magnetized. The magnetization is maximum. So this curve shows the same thing. On the x-axis, you are taking H. On the y-axis, you are taking B. B is basically coming from the magnetization of the material. So when your H is 0, the magnetization is 0. When you increase H, the magnetization increases, and then your magnetization becomes saturated. Saturated means all domains are in the direction of external field now. Now, if I increase H now, means this is at some value of H, which is some maximum value of H. So when you start decreasing H, again, the domains will get disoriented. They will cancel each other's magnetic moment and magnetization will decrease. But see here, at this point, your H is 0, but your magnetization is not 0. That means even when your H is 0, your external field is 0, there are few atoms which gets aligned in the particular direction. So your H is 0, but your B is not 0. Physically, this means that your magnet is a permanent magnet now. You take an iron piece, you place that iron piece into an electromagnet, you pass current through it, then you switch off the current, but still your iron piece is magnetized. It becomes permanent magnet. So this region here is known as retentivity. This is known as retentivity, residual magnetism. So a permanent magnet, for a permanent magnet, this region should be very large. Now, if you want to make your H to be 0, then what you will do, you will apply H in the opposite direction. You want your B to be 0. You want all domains to get disorientated like here. So you'll apply some H in the opposite direction. So this is the value of H and your B will become 0. This value of H that you apply to reduce your magnetization to 0 is known as retentivity. Coercivity, sorry. So if you have a permanent magnet, you want to destroy its magnetic field, you will apply some current in a direction opposite to the original direction. Then it will become non-magnetized. This is coercivity. Then again, if you increase H in this direction, then the magnetization will increase and it will again get saturated. The whole system will repeat itself. This is known as hysteresis. This loop is hysteresis. The area of the hysteresis loop represents the energy loss. Greater the area, greater will be the loss in energy. So this is important. You should do this comparison. These are conceptual questions that can be asked. Hysteresis loop we have already discussed, and this is yes. This comparison is very small. You will read it yourself. Okay. There are questions in PYQ from this comparison. That was about this chapter. So the majority of questions that comes from this chapters are theoretical, based on hysteresis, based on these properties, based on the selection of magnet as permanent magnet or temporary magnet or electromagnet, what type of material you will use. So I'm along with these notes, I'm sharing one small notes also for hysteresis. Along with this, I'm sharing one more thing on hysteresis. So that will have very detailed discussion of electromagnet, permanent magnet, and temporary magnet. That's all. So your syllabus is over. So what you want to do now? You want to terminate the class or you want to do some numericals?
So numericals.
Numericals, okay. Fine, I will share a schedule on group of how we will be solving the numericals. Okay. The chapters and the book from which we'll solve numericals. We'll start the revision from the chapter number 1 onwards, maybe electrostat and potential. And during that revision, if you have doubts in any specific topic, you can just text that doubt on the group and I can discuss the theory also. But majorly, I will focus on numericals. So I'll stop here. We'll start this on next week. If you have any doubts, you want to discuss something, I'm available. Otherwise, class is over.
Thank you, sir.
Sir, those examples for the magnetic for diameter